Welcome. As a part of the course EE 5110 Probability for Electrical Engineering, in this lecture we will cover the random experiments, the notion of sample space and events. Okay. So we are primarily interested in characterizing what are called as random experiments. Random experiments are experiments in which the outcome of the experiment is not known in advance. So the outcomes are non-deterministic. That does not mean we carry out the experiment in a random manner. Indeed, the experiments are of such a nature that they can be repeated precisely, but the only thing is their outcomes cannot be predicted in advance. There can be many outcomes that can happen, among which one will happen, and unlike in the case of the deterministic experiments, their outcome cannot be predicted in advance. However, we assume that there is some physical phenomenon underlying these random experiments which give rise to these outcomes, and they do not change, and henceforth we can do what is called as the statistical characterization of these random experiments. The precise meaning of statistical characterization is what we will be seeing in this lecture, and it will become more and more evident as we go through this course. So instead of there are other terminologies also being used for this notion of a random experiment. One such terminology is a trial. Trial is nothing but conducting of the random experiment once. One more terminology that can be used is a sample. That is, sampling is nothing but doing this random experiment. In the case of experiments such as throwing of a dice, then trial is a more appropriate word because we conduct this experiment and we look at the outcome. There are other such random experiments wherein we observe a physical quantity and look at the characteristics of the physical quantity, in which case sampling would be more appropriate. For example, if we have a box of resistors and we pick one resistor and look at its actual value of resistance, then here we are taking a sample and we observe certain physical quantities. In this case, sampling would be a more appropriate word. So in this course we interchangeably use the word trial or sampling in place of random experiments. Well, although the outcome of the random experiment is random in nature, we assume that all possible outcomes of the experiments can be found out, and one such outcome is what we call as the sample point. So sample points are nothing but one possible outcome of the random experiment. We also assume that all such sample points can be found out, and we can construct what is called as the set of all sample points. We call that as the sample space. So a sample space is the set of all outcomes of the random experiment. Well, we will see some examples of such random experiment, but in many cases we will see that the sample points of a random experiment are not observable as such, or we may not just be interested only in the sample points, in which case it may be meaningful to define what are called as events. To give some examples, let us say if you conduct an voting, okay, and there are a number of people who vote for a particular candidate, at the end of the voting process, typically what is being given out is the total votes acquired by one candidate versus the other candidate. So here the actual voting exercised by individuals are not even being revealed and it's not being observed. So rather we are only interested in finding the total votes acquired by a given candidate, and that is what of interest to us. Okay. So many cases we may not just be interested in which sample point has actually occurred, we are rather interested in what are called as events which carry certain meaning for the purpose for which we do this experiment. So therefore we define what are called as events. An event corresponds to nothing but a subset of the sample space. That is, if one or more sample points can occur, then we refer that to be an event. So we go on further to just look at few examples of the random experiments. All the most familiar example is the flipping of a coin. So if you flip a coin, which can be let's say a fair coin, there are two possible outcomes, the head and the tail. So we can give a shorthand notation H to denote the head and T to denote the tail, and the 2 possible sample points of this experiment is the set H comma T, and we denote it by a set capital omega. So here the capital omega is the sample space of the coin flipping experiment, and the 2 sample points are denoted as H and T. We can construct another experiment which involves flipping a coin twice and looking at the outcomes of both these coin tosses, and we can construct a pair in which the first outcome of the first experiment followed by the outcome of the second experiment is denoted together. So the set of all possible outcomes in this case would be a head followed by an head, head followed by a tail, or a tail followed by an head, and a tail followed by a tail. So that can be compactly denoted as HH, HT, TH and TT, and together these 4 sample points will constitute the sample space of the experiment wherein a coin is flipped twice. Okay. So there are many possible subsets of this sample space that we can construct, and each one of that will constitute an event. Okay. For example, if you are interested in an event in which at least one head has occurred in 2 flips, then the sample points which give rise to this event are the one which is HH, head, or head and tail, or a tail and head. So that we can together refer to a set called as the set E. So E is an event which is nothing but a subset of the sample space. One more example is the angle, okay, in the elastic collision that you observe in between a nuclear particle. Okay, so if 2 particles collide, if we may look at the angle of deflection of one particle, let us say a smaller particle in comparison with the heavier nucleus and so on. So the angle can lie between minus pi and plus pi, in which case the angle is a continuous valued one, and this may constitute the sample space. If we are only interested in an event where the angle lies between a particular range, let us say minus pi by 4 and plus pi by 4, this will constitute an event. So event is nothing but a subset of the sample space. So E is a subset of omega. Let's look at one more example. Suppose we roll a 6-sided die and observe the number of the dots on the side facing upwards. So this will constitute a random experiment. So the number of dots that can occur can lie between 1 to 6. So there are 6 sample points here. I can denote an outcome or a sample point, and the sample space is nothing but the set 1, 2, 3, 4, 5 and 6. Each subset of S is an event. Some examples of the events are the following. Let E1 be an event that corresponds to roll a rolling in such a in an experiment where a value 4 or higher occurs. So this set 4, 5, 6 will correspond to the event E1. Let E2 be an event that corresponds to getting an even numbered value. So 2, 4, 6, that set corresponds to E2. Similarly, if you look for an event where the number that occurs is a square of an integer, then only the possible even sample points that will give rise to this event is 1, 4. Many such random experiments can be thought of. Okay, we will just list out few of them. We will be seeing a lot more such random experiments and characterize them in this course. Drawing of a card from a deck can be a random experiment. Out of the 52 cards you may get one, and then even can be looking for a king or looking for a clubs and so on, or a black colored card and so on. The another experiment can be drawing of a ball from an urn having balls of different color. Suppose you have an urn which is nothing but a box in simple terminology, having let us say 4 red colored and then 3 blue colored ball. You pick up a ball at random and look at its color, and that can be the random experiment we are talking about. Or it can be height of a person that you measure, or it can be the measure of the rainfall that you see in a particular city during a monsoon season, measured in some quantities like height of in centimeters. Or it can be the strength of a signal that you observe in a mobile at a particular point in a city. Well, so we are going to use heavily the set theory in order to describe the sample space, sample points and the events. So we will briefly recollect some of the notions of the set theory. We will all be familiar with that one. We will try to correlate the set theoretic terminology with the terminology that we will be using or introducing for the purpose of constructing a probability theory. Okay, so a set is nothing but a collection of objects, well-defined collection of objects. It can be a concrete or abstract objects. Okay, so in probability theory, a set is nothing but an event, or for every event we can define a set. Okay, so we are particularly interested in sets of all outcomes of the random experiments, and we are interested in subsets of those sets and so on. Okay, so the set of all possible outcomes of the random experiment we denote it by the set capital Omega. So, and we call this as the sample space of the random experiment. Sample points are nothing but the individual outcomes of the experiment. We can introduce the notion small omega for that, and different terminologies can be used. Small omega is a way usually it is being denoted. And events are nothing but subsets of the sample space. You can note that in particular the entire sample space itself, okay, is maybe an event of interest to us. And you can see that if you conduct a random experiment, one of the subsets, sample points from the sample space has to occur. Therefore, the sample space corresponds to a sure event or a certain event. It should always occur. Similarly, if you define an event, okay, which corresponds to an impossible event, then no sample point should occur. Okay, and which means that we are talking about the empty set, which is a subset of the sample space. Okay, then given two sets, the union of the set can be defined. E and F are two sets. E union F, or sometimes written as E plus F, although we won't be using this notation often. If the set of all elements that are in at least one of the two sets E and F. For example, if E is given by the set 1, 2, 3, 4 and F is given by the set 1, 3, 4, 5, 6, then E union F is given by what is given in this slide. Then if E is a subset of F, we indicate it by the symbol E being a subset of F. Okay. So in the case of the events, a subset of F corresponds to an event such that some of the sample points of the F constitute the set E, which means that if the event E occurs, it implies that the event F has occurred, but not otherwise. Okay. Clearly, if E is a subset of F, it follows that E union F is equal to F. Okay. We indicate that psi is an element of omega by using this symbol psi element of omega that is given in this place. Okay. And then more concrete set theoretic notation, we define E union F as this one, set of all elements such that E is either an element of E or an element of F, or in our terminology, if E is an event, F is an event, E union F is an event such that it constitutes the sample points, all such sample points psi omega, such that this is a sample point corresponding to the event E or corresponding to the event F. Okay. Here the R is an inclusive R. Obviously this union is an commutative, has a commutative property. E union F is F union E. Then we can go about and define the intersection, or sometimes called as the set product of two sets E and F, denoted by this symbol E intersection F, or sometimes simply as EF, wherein this symbol is an implicit one. Okay. So this corresponds to the set of all elements that are common to E and F. Okay. So if you conduct an experiment and by E intersection F we represent an event in which both the events E as well as F has occurred. Okay. We will see some examples for that soon. So in set theoretic notation, E and F corresponds to all that elements or the sample points such that omega is the sample point of E as well as the sample point of F. Okay. Then given an event E, we can define the complement of the event E, that is, it corresponds to all the sample points which are not present in E, or set all elements in E should not be present in the set E complement. Okay. It can be easily seen from that E union E complement should be equal to the sample space omega, and E intersection E complement should be equal to the null set or the empty set psi. We can define some more set operations. The set difference of two events, or more appropriately the reduction of E by F, is written as E minus F. Okay. It corresponds to the set of all elements in E, but they should not be present in F. All those elements in E which are not present in F corresponds to E minus F. Okay. So there is an alternate way of arriving at the set E minus F. So it can be seen later on using a Venn diagram that E minus F is nothing but E intersection F complement. So F complement will exclude everything that is in F, and we are looking at everything that is not in F but present in E. Similarly, F minus E can be written as F into E complement. So obviously the set we can, this kind of an, it should not be confused with the subtraction with which we are all familiar in arithmetic. For example, f minus e is nothing but f minus e. Okay, so there is nothing like f minus 2e. So we have to be very careful in using these set theoretic operations. The exclusive of two sets denoted as f exclusive f is the set of all symbols in E or F but not in both, and that can be written in the following form: E exclusive or F is nothing but E minus F union F minus E. We can also see later on using Venn diagram how this results hold good. Okay, so Venn diagram, as you know, is a very pictorial way of looking at how set theoretic operation takes place. Again, we will make use of it or leverage it to interpret our various operations that we carry out on events, and talk about the various event related operations, so on. So let E and F, suppose this entire corresponds to the sample space, then all the elements that are present in this square constitutes the various sample points of the sample space. So if you collect certain sample points and define an event, so that can be represented by means of a circle like this one. So E is an event which is nothing but a subset of this sample space. F can be another such set. So this represents the union operation, whereas this represents that both the event E as well as event F should have occurred, which means we are only talking about the sample points which are common to E as well as F. So that will be present in this shaded area. When E is a event which is a subset of the sample space, E complement is the complement event, so that will be everything outside E but within the sample space. So here we can easily see that E minus F is everything in E but which is not present in F, so that will correspond to this shaded area. Similarly, F minus E can be given like this one, and we can see that E exclusive or F is given by this shaded area. So here it is nothing but the E intersection F is not included. So this is what will later on we will translate to, as we will see that probability of E union F is nothing but probability of E probability of F minus probability of E intersection F can all be derived using this. Okay, and we will see some more things, operations. Well, two events E and F are said to be disjoint is if E intersection F is a null set, that is, they don't have any elements in common. Then given an event E, we can form what is called as the n partition of E, consisting of a sequence of events. Let us call each one as EI. So where I, the index I, can range from 1 to n, such that every such subset EI, every such set EI is a subset of E. In addition, the union of all such EI should correspond to E, and EIs are such that they are mutually disjoint. Written in another way as EI intersection EJ is a empty set for all I not equal to J. So what we are essentially doing is we are taking a set and we are partitioning it into mutually exclusive, collectively exhaustive sets. Okay. For example, if you have two sets E and F, if you want to partition F and construct a two partition, okay, then we can easily see that FE and FE complement are two partitions of F, in the sense that F is Fe union Fe complement, because if you do an intersection of this one, Fe intersection Fe complement will be a null set, because E and E complement intersection is null set. If in addition, if you look at F intersection E and F intersection E complement, their intersection will also be a null set. So therefore these two constitute a two partition. Then using the Venn diagram, it's easy to construct and derive what are called as the De Morgan's law, that is E union F whole complement is nothing but E complement intersection F complement, and similarly E intersection F whole complement is equal to E complement union F complement. Probably using the previous Venn diagram, we will be able to see that here you can see that maybe in a later Venn diagram I will show you how this results can be arrived at very easily using the Venn diagram approach. We can also generalize the De Morgan's law for a number of sets. Let us say if we have sets E1 to En, then this is union of a number of sets n such, union of I varying from 1 to n Ei, and if you perform a complementation, that is nothing but intersection of I varying from 1 to n Ei. So that's missing here. So here also there is something missing. Okay. Similarly, the intersection of I varying from 1 to n Ei whole complement is union of I varying from 1 to n Ei. Okay. So having looked at some of the set theoretic formulation, we can then again reformulate our understanding of the random experiments, the notion of sample space, sample points, events in terms of that. Okay. So again, to recollect what we talked about, a random experiment is, or a trial is a one in which the outcomes cannot be predicted. The set of all possible outcomes is called as the sample points, omega 1, omega 2 and so on, or the sample points. And sampling is nothing but conducting a trial or performing a random experiments and looking for an outcome. If you look at a coin tossing, there are two sample points. Omega 1 is the occurrence of head, omega 2 is the occurrence of the tail. So the sample space is h comma t. For the case of rolling of a die, there are 6 sample points. We can denote it as omega 1, omega 2 to omega 6, are nothing but the phases 1 to 6. So the set of all possible outcomes of the random experiment constitutes the sample space, denoted as capital omega, whereas the sample points are denoted using the small case omegas. So for the case of coin toss, h comma t is the sample space. For the rolling of dice, 1 to 6 is the sample space. We define the sample points are nothing but the elementary outcomes, such that each outcome is elementary in the sense that occurrence of this outcome excludes the occurrence of any other outcome that corresponds to a sample point. That is, only one of the sample point can occur when you conduct an experiment. An event is nothing but a case in which we are interested in, and that constitutes a set of all sample points, which is a subset of the sample space. So a certain set of elementary outcomes, we call it as the event E. Then, so every such event which is a subset of the sample space has to be a subset of the sample space, which is what is denoted here. So what we now do is, in order to construct the notion of probability and so on, we put some structure into the set of all events on which we are going to define, okay, what are called as the likelihood of the occurrence of events. So because the random experiments leads to outcomes which cannot be predicted. At best, what we can do is to tell what are the odds of an outcome to occur or an event to occur, or in more common sense, what is the likelihood of an event to occur. We will formalize it and we will use the term probability to denote this odds of the event or the likelihood of the event and so on. So in order to define that notion of probability, we are interested in certain events, a collection of events which should satisfy certain properties so that the whole formalism becomes more meaningful. So if we have a sample space, we can think of a number of events that can be constructed out of this sample space. Okay, so the collection of all such possible events within a sample space is nothing but the power set of the sample space. Okay, if there are n elements sample points, there are 2 power n possible events that we can define, but all those events may not be of interest to us. We may only be interested in certain events for certain purpose of our discussion. So let us say E1, E2, E3 are certain events in which we are interested. Obviously they should be subsets of this of a collection of events which we want to talk about. We will give a representation or a notation F. So F is a set of sets, or more clearly a collection of sets. Okay, now the structure that we want to bring in is as follows. Suppose we know there are 2 events E1 and E2 in which we are interested in, which means that we should be able to tell what is the likelihood of occurrence of event E1 or the event E2. Then it makes sense to ask the question, what is the likelihood of occurrence of either event E1 or the event E2. We should be in a position to tell the corresponding odds also. Otherwise it doesn't make sense. We can only tell about the odds of the event E1 and E2 alone, but nothing about their union. So we expect that if E1 and E2 are 2 events which are present in the collection F, E1 union E2 should also be present, which means this collection F should be closed under the set union operation. One more logical thing that we can talk about is, if you can tell about the odds for the occurrence of the event E1, you should also be able to tell what is the odds that the event E1 does not occur. Okay. Therefore, if E1 is an element of F, then naturally E1 complement should also be an element of F, which means that this collection F should be closed under the operation of set complementation. So together we are looking for a collection that is a set of all possible 1 minute, let me zoom it. Yeah, we are interested in constructing a collection of events or the sets, okay, or a class of events F such that it is closed under the set union and set complementation operation. Indeed, the class F should be closed under finite number of set union operation and set complementation operation. Such a class, we call it as the sigma field or a sigma algebra, denoted in this manner. So we construct what is called as a sigma field out of the events that are interest to us, and we will then go ahead defining more formally the odds of occurrence of such events, or what we will call it as the probability of occurrence of that events. To get a better understanding, we will just look at certain sigma algebras for certain random experiments. Let us say you have a coin tossing experiments whose sample space capital omega corresponds to h comma t. we can define all possible events that can occur in this sample space. That is, all possible subsets of omega, which is H alone or T alone or H comma T or the empty set. We can see that this is closed under the operation of set union and set complementation. Indeed, as we will see, it will also be closed under set intersection operation. You would see that H union T will corresponds to HT, H union HT corresponds to HT, T union empty set will corresponds to HT, and so on. Similarly, the complementation of H is T, complementation of T is H, and the complementation of the sample space is the empty set, and vice versa, and so on. So this is a special case in which all possible subsets of the sample space is present. But suppose we are only interested in certain events, okay, and we want to construct a sigma algebra wherein these events of interest to us are present. Let's see how it can be done. Suppose we look at an experiment which is the rolling of a dice. The sample space omega corresponds to 1, 2, 3, 4, 5, 6. Let us say we are interested in the event of occurrence of an odd number in the rolling or the even number. Then the event of occurrence of odd number corresponds to the set 1, 3, 5. For the even event, it corresponds to the set 2, 4, 6. Then obviously we should first introduce these two sets within the sigma algebra. Then it should be clear that the sigma algebra should constitute always the entire sample space, even though the individually the samples we are interested is not their union may not generate, but we will always introduce the entire sample space as an element of this sigma algebra, because obviously we should always be able to tell what is the likelihood of the entire sample space to occur, okay, because it is a sure event. Again, because it has to be closed under set complementation, if omega is an element of F, omega complement should also be element of F. So we will always introduce this sample space as well as the empty set to always be present in F. Okay. Now if you look at these two events, so we introduce these two events. In addition, we also introduce the sample space as well as the empty set. Now we should not stop at this point. To be more logically consistent, we should check whether this sigma algebra is closed under the operation of set union and set complementation. It so happens that in this case it is closed under these two operations. For example, the complement of 135 is 246 and 246 is this. If you take an intersection of that, you will get an empty set. If you take a union of that, you will get this one. If you take a union of the sample space and 135, you will get back the sample space, and so on. It goes like that. Sometimes what we may have to do is that to construct a sigma algebra, we will just introduce the events that is of interest to us, and also the sample space and the empty set, and then take two such events and then check whether its union is present. If it is not present, we will introduce it. Similarly, we will check whether their complement is present. If not, we will introduce it. So we will introduce additional elements into the sigma algebra, into this collection F, until it becomes a valid sigma algebra. Okay. So again, we will see that Venn diagram can be very easily used to understand the various operation on the sets as which corresponds to the event. So A union B is the case where both the either one of these events A and B, or both event A and B has occurred. Okay, this A intersection B corresponds to the case where both the event A as well as B has occurred, and this is A complement, and you will see that this is B complement, everything that is not present in B. So here you will see that if you take a intersection of A complement as well as B complement, so A complement has everything other than A, B complement has got everything other than B. So if you take a union of this one, you would get this. So this, you can easily see that this is nothing but A union B whole complement, and this is what the De Morgan's law is, which I mentioned that it can now easily be seen using Venn diagram. So we have, in a similar manner, there are two De Morgan's law, both can be easily understood using Venn diagram. A union B whole complement is A complement intersection B complement, and so on. Similarly, A intersection B complement is this, and the generalized De Morgan's law can also be written like this one. So at this point we complete our discussion on the random experiments, what are called sample points, the sample space, the events, and the sigma algebra constructed using this event space. Okay, we will call this event space or the sigma algebra. We call the sigma algebra as event space, and with all these ingredients ready at our hand, the next thing that we have to do is to introduce the notion of probability, wherein we assign a measure for the likelihood of occurrence of an event. So I will conclude this lecture at this point. Thank you.